Hi everybody, this is the next in a series of lectures around fluid mechanics, and in this case we're going to look at the pressure a fluid can actually apply. To start with, the definition of pressure in general is a force applied over a specific area. So an equation for that is just that. It is the force applied to that specific area. And pressure in metric is measured in a standard unit called the Pascal. It's also the same thing as the Newton per square meter. So for example, talking about the pressure a solid can apply, which we want to sort of understand before we get into the ideas of fluids, a reminder of this, is if I've got a 4 kilogram cylinder with a radius of 3 centimeters and a height of 6 centimeters and it's sitting on a table, and I just want to know how much pressure it's applying to the table. Interestingly, the height of the cylinder doesn't really matter because it's only the pressure is applied where the contact is made, which is down at the table. So in doing this, if pressure is going to be force over area, well, what kind of force is it going to apply? Well, obviously, the force is due to its own weight pushing down there. So in this case, we can replace force with the weight of the cylinder. The area, again, is the area of contact, which is the circle part of the cylinder. So as far as the area goes, we need just to do the area of a circle, which of course is pi r squared. So it's pretty simply plugging in. We have the mass of 4, gravity of about 10, and a radius of 3 centimeters, which is about 0.03 meters, which gives a pressure of 1.41 times 10 to the 4th pascals, about 14,000 pascals. And again, pressure numbers tend to be rather large numbers in terms of pascals, so there's nothing wrong with that. So that's the idea of just what a pressure, what a solid was going to apply. Now, one of the most interesting fluid pressures is one that we sort of take for granted every day, and that is called the atmospheric pressure. Literally the pressure that the air puts on us just due to us living here on Earth. And atmospheric pressure at sea level is about 1.01 times 10 to the 5th pascals. So again, a very large amount of pressure when you think about it. You know, if you're holding that cylinder we talked about before, you can feel the weight of that very easily. But we don't feel the actual weight of air that's acting on us, but it's pretty significant when you think about it. So let's look at how significant it actually is. So the Earth's atmosphere stretches very far, over 500 kilometers or so, but 90% of the atmosphere is actually in the lower 16 kilometers of the air. It gets much, much thinner as you go up. So the human head has about an average radius of about 8.5 centimeters. So let's figure out how much force is actually being applied due to 16 kilometers of air pressure sitting on top of us. Now again, that's assuming it's really uniform, and that's close enough. So again, pressure, force over area. So the force applied to the surface of our head would be that air pressure times the area it's being applied to, which would be the sort of radius of our head. So we have air pressure of 101 kilopascals, 1.01 times 10 to the 5th, times pi r squared, which gives a force of 2,292.5 newtons. Now, that's a significant amount of force when you think about it. When you think about the weight of an average adult is somewhere around 800 newtons. This is 4 times or so about the weight of an average adult sitting on top of your head. Yet we don't really notice that because, of course, we've evolved in this atmosphere to not really notice that. But it's a pretty significant amount of force. So imagine what would happen if you were to go swimming and diving under the water. Because now you're going to have the pressure of the water that's going to be around you. So that's another fluid addition to the air. So we want to look at something called the idea of your absolute pressure, which is whenever an object is immersed inside another liquid on Earth, what kind of pressure is it truly feeling? Absolute pressure is based on the atmospheric pressure and on the pressure due to the density of the surrounding fluid you happen to be immersed in. Now, that pressure also depends on how deep into the fluid you actually are. And so to figure out how much pressure just from the fluid location, that's going to depend again on sort of what your depth is inside the fluid. Then, once we know that value, we can determine what the absolute pressure is acting on something. So for example here, I've got a tank of water that is 3 meters deep. Now, for the moment, I'm going to turn the atmosphere off. And so, of course, with no atmosphere, there would be no pressure at the surface. I go down 1 meter and I get about 10 kilopascals of pressure. I go down 2 meters and it doubles to 20. So you can see there's sort of a directly proportional relationship. Okay? For whatever factor the depth of the water goes up, the pressure goes up by that same amount. However, if you switch the atmosphere on, now you'll notice there is significantly more pressure. And that's simply because we have the pressure of the air itself before we get into the tank, plus the additional pressure due to the water level itself. So as you can see, that air pressure adds on to the total pressure you're going to experience. So let's say you decide to go diving into the ocean. And ocean water has a higher density than fresh water at about 1,030, which is why ships often have two water lines on them, cargo ships, one for when they're sailing through fresh water and one when they're sailing through ocean water. As the ocean water having a greater density is going to be able to apply more force and more buoyancy. So if you have a diver who is simply down 10 meters, so a little more than 30 feet, a typical dive that a lot of people will go into the ocean, and we want to look at what their absolute pressure is going to be. Again, the absolute pressure is the atmospheric pressure plus their pressure due to the fluid. And so that would be the absolute pressure plus this rho GH. Now, H being really depth, not so much height, but really depth. So even though, let's say, this part of the ocean is 60 meters deep, the height wouldn't be 50 meters. It's more of a depth of 10 meters. So the pressure this diver would feel would be atmospheric pressure, 1.01 times 10 to the fifth, plus, we have a density of 1,030. Gravity is about 10, and the depth here of 10 meters. Again, that is the height that we're talking about. It's really a depth. And so the pressure the diver feels there is 2.04 times 10 to the fifth pascals, which you'll notice is about double what the atmospheric pressure is. So just going down 30 feet into the ocean increases your pressure twice as much as you would feel out in the normal air. Sometimes this would be referred to as 2 atmospheres of pressure. That's a common term. Atmospheric pressure, when you're on the air, is just simply called 1 atmosphere. So you would be feeling 2 atmospheres of pressure. Now imagine you go down another 10 meters. You're probably going to get 3 atmospheres of pressure. So the deeper and deeper you go, the stronger the pressure is going to be on your body. Now that has some physiological effects that can result in the bends if you come up too fast, but that's a whole nother story. So one last thing to discuss here around the idea of fluid pressure is something that is called gauge pressure. So for example, if you've ever gone to inflate anything, it'll tell you to inflate it to a certain pressure. A soccer ball needs to be inflated to about 8 psi, which is pounds per square inch in English term. Typical tires have to be inflated to a certain pressure. Well, you know what pressure to inflate it in because you have an actual gauge that you're looking at in which to inflate it with. But here's the interesting thing. If you have a flat tire, the reason it's flat is because the air has leaked out of it until it's reached equilibrium. But the equilibrium it's reaching with is the atmospheric pressure. Now the only way for this tire to have stopped expelling air is if the air inside is equal to the air pressure outside, which means inside is already atmospheric pressure. So gauge pressure is simply the difference between the absolute pressure and atmospheric pressure. In other words, gauge pressure is when you sort of subtract out the atmospheric pressure. And that's what it'll tell you on the gauge. Say an average car tire is inflated until the tire gauge reaches 32 psi, about 220 kilopascals. We want to determine what the absolute pressure is inside the tire. Now again, think about this. The tire has to have an internal pressure greater than the atmosphere in order for it to inflate enough to be able to hold on to that pressure. So as I talked about, when we have a flat tire, the pressure inside the flat tire, the absolute pressure, is atmospheric when it is flat, okay, because that's an equilibrium. Otherwise, air would be moving in and out of the tires still. Okay, so air moves until you reach sort of an equilibrium. The absolute pressure would have to be the gauge pressure plus the atmospheric pressure that's already in there. So this is really actually pretty simple. The absolute pressure would be the gauge pressure, 220 kilopascals, or 220 times 10 to the third pascals, plus the atmospheric pressure, 1.01 times 10 to the fifth pascals, which gives an absolute pressure of 3.21 times 10 to the fifth pascals. By the way, this is the same thing as saying 321 kilopascals. Kilopascals is often sometimes an easier way to express pressure. And that's a simple idea of how we relate the idea of a gauge pressure and an absolute pressure. So again, keep in mind that gauge pressure is when you take atmosphere out of the equation. Absolute pressure is when you have to include the gauge pressure. Okay, so that's the idea of how fluid pressure actually works, which is going to be important to some other ideas that we work in here as we talk about fluid mechanics. All right, see you next time.